Okay, so far we've talked about how to solve an equation or how to solve a system that looks like this, where we have ax is equal to b, and when we were trying to solve the system, we had the a, it was the coefficient matrix, x was the unknown, and the b was the answer vector. And wait a second, okay. And when we try to solve this, we remember that we try to obtain the reduced row echelon form. Okay, so we were trying to get this this reduced row echelon form using elementary row operations. So this would be the elementary row operations. Now, this keyword, elementary row operations, it is very essential because it preserves the information that was initially given or that is initially represented by a matrix. Okay, so only if we use elementary row operations, we can preserve the initial information. Because as we are applying the elementary row operations, we are trying to remove the redundancies in the data or in the explanation. And how the way to do it, we try to get this by producing a lot of zeros. So whenever we can simplify some expressions, whenever we can reduce the number of coefficients in the coefficient matrix, that's what we are trying to do. If you remember it well from the last session meeting, we used to report to find some pivot elements, which are the leading elements at each pivot row. And we used to make those ones, and we try to make all the entries in the matrix below and above the pivot elements, we try to make those zeros. Now, so these elementary row operations, we don't have many of those. So the first one is we can multiply any row with a constant. The second one is that when we interchange row I, we interchange with row j. So we can do this. We can take row fourth, we can replace it with row 1, or we can change the places. And the final row operation is the following. So we say that row j star is equal to row j minus delta row I. Okay, and this is the pivot row. This is the pivot row, and and this is the row that will be affected. This is the row which will be changed. So these are the elementary row operations. And for example, we have a couple of examples that we can go here. And we can define an elementary matrix. An elementary matrix, it's a matrix So elementary matrices, they are the ones that are modified from an identity matrix using elementary row operations. So using these, we can obtain an elementary matrix. For example, we have a matrix here 1, 0, 0, 3, 1, 0, and 0, 0, 1. So this is an elementary matrix because we can obtain this from an identity matrix where the identity matrix is the following. So this is identity. And here we can obtain this one by doing this operation. We can say 3 row 1 plus row 2 is equal to row 2 star. Okay. So using this operation, we can get this matrix. So we call this one an elementary matrix. So this is EO. Sorry, EM. So if this is the definition of an elementary matrix. And these elementary matrices, in fact, we use these because they are like transformations, or they represent a transformation from one matrix to another. For example, let's see, we need some space here. So what we mean with this is the following. So let's give a matrix A, which is equal to, let's say, 2, minus 1, 0, 7, minus 8, 5, 1, minus 1, 2. Okay, so here we have a matrix, and with elementary matrices, what we mean with this is a description in a matrix form of such a entry. Okay, so we said that elementary row operations, there are 3 types. We multiply a row with a constant, we exchange 2 rows, and we use this operation. So now, for a moment, let's multiply this matrix A by this elementary matrix, and let's see what we get. So let's multiply here. This is, you can see this, it's 1, 0, 0, 3, 1, 0, 0, 0, 1. So if we multiply these together, we get 1, 0, 0 times this column. We get here 2. 1, 0, 0 times here, we get minus 1. 1, 0, 0, we multiply this column with this, sorry, this row with this column, we get 0. And then we have 3 times 2, 6 plus 7, 13. And then we get minus 3, minus 8, minus 11. And then we get 5. Then we have the following, 0, 0 times 1. Oh, we got this, okay, this is relatively simple. So here we get 1. Sorry, this is empty. Allow me, okay, so I made a mistake, this is just minus 1. So we can pick up a number, which would be minus 3, okay? Sorry about that. So here we have 0, 0, 1 times, we get here 1, minus 3, and 2, okay? So this is the matrix A, this is the elementary matrix EN, and this is the result. Now, what does this represent in principle? Let's check the following. What is, so we see that how has this matrix changed? This A star, what is the relationship of A star with A? We see that the first row is the same, the last row is the same, okay, so they are the same. Only this row has changed. But how has this changed? We look at the numbers, and it looks like this row, that is the only one that is modified, that is changed. This is, let me think for a moment. Yeah, so this row 2 is in fact, so this row here is this row plus 3 times this. So we can say row 2 star, which belongs to this one, is equal to row 2 plus 3 row 1. And row 2 and row 1 belong to here. So let's check if this is true. We get here 7 plus 3 times 2. 7 plus 6 is 13. 8 minus 3 minus 11. 5 plus 3 times 0 is 5. Okay, that's good. So it looks like these elementary matrices, what they are elementary and they represent this expression. Only that we, all this operation that we do, we don't write it like this, but we use it like an operator. Okay, so this is equivalent. For example, we have, let's assume that we have in mathematics, we have a function, we have a variable x. Okay, then you apply g of x. Okay. Then to this new variable, you apply another function or an operator, linear operator, f the g of x and f of g of x. We can also call this one like FOG, f of g of x. Okay, so this is the language of the way we apply different linear operators from the output of the first. So we can have here another h. You can say, sorry, we can say here h. And this will become, sorry, this would be a little more modified. This would be h of f of g of x. Okay, so what is the equivalence of this with this is that we have a data which is represented in a matrix, and we apply an operator, but this operator is described by a matrix. And we have said before in this class that any linear operator that you want to do with a data set, you can represent it by a matrix. What does this mean? If the function is a matrix, that means that we multiply this matrix with another data set. Okay, so this is what we can say here. So let me give you an example, which it would be a good homework for you. Is the following. Imagine, let me tell you one number. So you are in front of a computer, you can use your cell phones and do the following, and I'll take 2 minutes from your time so that you might get kind of impressed, okay? So get this number, from 1 to 9, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the first 9 students that will hear their names, please multiply this number, multiply this with numbers from 2, 3, 4, 5, 6, 7, 8, 9. Go like this. So you check in the class attendance in the names. So Aidina, you multiply this number by 2. Anna, multiply this number by 3. Aida, multiply by 4, and you find yourself. So all of you, at least up to 20. The first 20 students, please multiply this number with 2, 3, 4, 5, 6, 7, up to 20. Okay, which goes from Aidina, Andan, Alda, I cannot see this, Alexandro, Alisa, so go with it, okay? And I want your answers here on the comment section of the classroom. And I don't want you to say, am I the third or the fourth? So please just do it. Muguptuat para Aidina, Alan, Aida, Alexandro, Alisa, Andi, Ardisa, Ariola, dear. So I'm waiting here. So all you need to do is multiply this number by these numbers, okay, and keep it in your calculator and enter it there. And what I want from you is the following. So what you see here, you see each number mentioned only once, okay? Come on, I can expect, I can have volunteers enter this number. Okay, I have Aidina. Aidina, what do you see in your number? In your result, which is like 246,913,578. In this number, is any number repeated twice? You can answer, you can open your microphone, okay, to make
No.
this. No, okay. So here you have a permutation, okay? How do you represent this permutation of these numbers? Again, I'm waiting from the others. Who was the second? You should be faster. Volunteers from the class, or you can enter this multiplication over there, and I want you to see it. So Aidina did the first one, multiply by 2. Please, the third one, multiply by 3, by 4. If I don't get all the answers in like 30 seconds, you're going to get a very challenging midterm. Ardisa found something unique, okay? Go ahead. Aidina, you can multiply them. It won't take you a lot of time if the rest of the class cannot do it. Alexander, thanks, by 4. Okay. Then Alexander, open your microphone and tell me this result that you got. Do you have any number that is listed twice?
No.
No. Okay. So apparently it's just a permutation. Okay. What do we mean with a permutation? Is that you have a list of numbers and they're just you have exchanged
different combinations.
Huh?
They are different combinations, but
yes, there are different combinations. But so you have the same numbers. You just exchange your rows. Okay?
yes, the position.
Exactly. So what do we mean with this one is that initially you have 1, 2, 3, 4, 5. Sorry, I don't have much space, but allow me to write this once more. So you are given a vector, okay, which is 1, 2, 3, 4. And by the way, I'm waiting the answers beyond 7. Okay, please. It will be a good exercise. You're going to see an interesting property. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so here we have a vector. Okay, and now what does it mean to multiply this vector by 2? Okay, multiplying this vector by 2, it might be tricky to find it out, but assume that you multiply this one So let's say if it is a combination of the same numbers, you might know and you might write a program code regarding this. So let's see what is the answer of Kevin. Kevin is okay, that's a beautiful. Kevin result where he multiplied it by 11. Let me ask Kevin, do you have any one of the numbers mentioned twice or listed twice?
No.
No, but you have the 0, right?
No number was mentioned twice.
No numbers mentioned twice, but are all of these numbers in your result? So are all of these numbers in your result? So you have from 1 to 9. Do you have any extra number?
No, we don't have any extra number.
Well, you have a 0.
Okay. Yeah, we have a 0.
You have an extra number, that's good. So let's add 0 here. So let's add a 0 here, and let's try to identify how you can represent this multiplication of numbers or this array of numbers. How can you get your answer? Your answer, if I look at Kevin's answer, it should start like this. I have 1, 3, 5, 8. Okay, this should be. So first of all, this is a matrix, a vector, which is 10 by 1. Okay, and then I should get another number, which Kevin got it there. It was, what was it? 1, 5, 3. Wait a second. 1, 3, 5, 8. Okay. 1, 3, 5, 8. What is the rest? 0, 24, 6, 7, 9. 0, 24, 6, 7, 9. At one point, it becomes like a Sudoku. So they should find the number that you have not written it yet. Good. So this is another vector which is 10 by 1. So now, how can you multiply this one? How you can represent this one by matrix multiplication? Or we use it, our terminology of this course, using elementary matrices. First of all, it looks like 1, it has never changed place. Then we need to bring the 3 to here. Okay, so what you can do is that the first operation that you can do here, you can do the following. Row 2 exchange with row 3. Would you agree with this? Someone can confirm this?
Yes.
Okay, thanks. So if you want to exchange row 2 with row 3, up the 3 will come here, so we are done with this part. Up to here we are fine. But how can we do this with elementary matrices? To do this, we multiply this with a matrix which is going to look like this. 0. No, this is the first row. It doesn't change. 1, 0, 0, 0. It goes all zeros. Okay. Let's not forget this should be an identity matrix. How can we exchange row 2 with row 1? Let's put here 0, 0, 1, 0, 0, 0, 0. Here it's going to be 0, 1, 0. So this exchange of the rows, it can be represented from an identity matrix by just interchanging these numbers. So let's try if this is true. Let's assume for a moment that we have here matrix 1 minus 1, 5, 7, 1, 2, 2 minus 2, 1. Okay? And let's change here. This identity matrix, let's do it like this. This is, sorry, how should we do this? Row 2 and row 3, how can they exchange places? This is 0, 0. So what did we do to this elementary matrix? We exchanged row 3 with row 2. So we did this to this elementary matrix. So it is an EM now. Okay, this is an EM. We multiply with this matrix, what do we get? If you check the first row and multiply with this, we get 1 minus 1, 5. Then you multiply this with all of these, and you get here 2 minus 2, 1. You multiply with this, you get 7, 1, 2. So what did this identity matrix, where we change row 2 with row 3, do? So this becomes an operator. This becomes a linear operator or a transformation function, which in principle, we just multiply this EM with this matrix A, and it will do this nice operation. So this is what I'm trying to say, which in principle, you can see this multiplication of these numbers that you are correctly answered over there, of course using your calculator, but you could also do the following. It looks like most of the time, very few cases, you can even count how cases you have that a number is, so for example, 15, the result of Fabio, it's a unique place, unique case, because we see the same number repeating itself a lot. Okay, what is this? 185, 185, 185, 185, 3, something. But the rest, I think Fabio's number is different. Then you can pick up which one is other different. Anyways, like, oh, Ioni Daich's number is different. And also we had the multiplication by 3, good. But, so in this nice exercise, if you want to multiply these numbers, it looks like, what did we do? In order to do this exchange, or about this, you just have an identity matrix, and you interchange row 2 with row 3. Then, what do we need to do next? 3 is fine. Now, we need to bring, so it's hard even to keep track of this one. So this one becomes 1, 3, row 2 comes down here. What is the next step? We need to exchange the 5 to bring it up here. Okay. So what is the next operation? We need to exchange row 3 with row 5. So how can we do the next operation? We can follow like this. We draw again an identity matrix here. And the only thing that we are going to do in this new identity matrix is that for row 1, row 2, row 3, row 4, and row 5, these two, we just change the places of these two, and we perform the other permutation. Then we bring another identity matrix, which is 10 by 10, and we do the interchange. But how do we do the interchange? Identity matrix, we change the places of these rows, which we want to interchange. Okay, so I think this could be a good and to some degree intuitive example, which might also remind you of what we are doing. So this was only interchanging. At the same time, you can also interchange and multiply by a constant number. That is also, actually that one is not an operation. Interchanging is on itself, but then you can apply operations like these. Row 2 plus 3, row 1, etc. Okay, depending on what you want to do. Meanwhile, we also became aware of an interesting problem, which you can go on like this beyond the results of Fabio. If you keep multiplying beyond 15, you might observe very interesting properties of numbers, which, for example, what would be a good exercise for Lorentz, since Lorentz has also, each number is only mentioned once. What Lorentz can do is to find this elementary matrix that interchange the 2 and the 3. So let's assume for a moment we have this number from 1 to 9, adding the 0, that let this vector be vector x. Okay. Then the matrix that did the first interchange, row 2 with row 3, let's call this one EM1, elementary matrix 1. So we multiply this one with elementary matrix 1, okay? Then what happened next? We needed to interchange row 3 with row 5, okay? Let's call this elementary matrix 2. So all of these representation of changing the data set using this properties, this becomes another matrix. We multiply it, we call this one EM2, elementary matrix 2. And we multiply like this, and this space, we can make use of this. And then we go on as many, so then we have to multiply with elementary matrix 3, okay? It goes on like this. Of course, we're going to have few like these, elementary matrix 4. So all of these will be in permutation. And if you write a code about this one, it will be really a good exercise for you to figure out actually what is the total number of permutations. And now, what is also interesting is that all of these matrices and all of these are 10 by 10. Okay, so they are square matrices. What you can do is that you can multiply all of these matrices, and you can get, let's call the matrix EM times x is only equal to x final. Okay, let's do it like this. So there is a way, for example, let's say you want to multiply this number, you want to get this, right? How do you do it? You multiply EM1, EM2, etc. in the end, but you don't have a single matrix. A 10 by 10 matrix multiply this. How can you find it? You can multiply, for example, what we did here. You can see that you can multiply this EM1 and EM2, and you multiply them together, you find a combined matrix, which is also 10 by 10. And actually, for your group, this will be like a homework. You have to submit this one until, let's say, I'm going to assign some time. Just it's not a whole homework, but please multiply this vector with this vector and find EM. Okay, this is your EM is equal to. Okay. Okay, that's good. So now we spent a few minutes actually just to explain this exercise in order to raise a little bit the attention on how these elementary row operations are done. Okay. So in principle, that's most what we wanted to say. And now we move to another. But let me think for a moment. Okay. Now, okay, I can also add the following, which would be very useful, is the following, that these elementary row operations, they have also the inverse elementary row operation. And how would this be defined? For example, you can have, we can have, okay, let's give this matrix for a test. Let's assume that we have a row operation, which is row 2 star is equal to row 2 minus 4 row 1. And this is an elementary row operation, so this is equivalent to this, okay? Row 2 star is equal to. Then we have another, or let's call this one E1. Let be another elementary row operation E2, which is equivalent to reporting that row 2 star is equal to row 2 plus 4 row 1. Okay, so here we have two elementary row operations, and now let's try to identify what is this elementary row operation in a matrix notation. Let's start with identity matrix. Identity matrix, it is 1 0 0 0 1 0 0 0 1, and then E1 is going to be equal to what? Who can help me here? So any volunteer from the class? I don't thank you very much. You moved forward with 23. Okay, and it looks like even at 23, all of the numbers that you have, they are just listed only once. So there are only different combinations, and it looks like whenever we multiply this number with larger numbers, it's very rare that the number repeats itself at least twice. Okay, so mostly it looks like they look like permutations, and this is a good number theory problem that you can work on it. Good. So what is elementary matrix E1? How do we find this? How did we find, let's say, the matrix representation where we interchanged row 2 with row 1? We just put the identity matrix, we did it. Let's try to do it here. So this is not changing, but then we apply this operator on the identity matrix, okay? So if we apply this on the identity matrix, we get the matrix representation of the elementary row operation. So this is row 2 minus 4 row 1. How would this be equal to? This is row 2 is 0, minus 4, we get minus 4, and this is 1, 0, 0, 0, 1. Okay? Now, it is, I can delete this part. Now, okay, we found this. And actually, let's try to identify what is E2. E2 is now, the first row is not changing. So let's not forget, these three elementary row operations, which are possible only three of those, we're doing the changes on the identity matrix, okay? So an elementary matrix, which we wrote on the board as EN, is one that has undergone, let's call it only one linear function operator, change of the rows. So let's say that row 2 star is equal to, let's do it on here. So here we get 4, that's 4, right? Okay. 4, 1, 0, thank you. And this is 0, 0, 1. Okay. Then, now we can try to do the following. So here we have this nice matrix. Let's keep this here. And let's multiply this one with E1. 1, 0, 0, minus 4, 1, 0, 0, 0, 1. What is this equal to? Okay. 1, 0, 0, if it multiplies, this will be the same. Okay. Then here we have minus 4. Okay, minus 4 times 2 is minus 8 plus 7 minus 1. You can correct me if I make any mistake. Minus 4 times minus 1, it's 4. Minus 8 minus 4. And then we get minus 4, 1, 5. And then we have 0, 0, 1. We get here 1, minus 3, 2. Okay, so we started with this matrix A. Let's call this one matrix A. And we multiply it with this value. This we multiply it with E1. So this is equal to E1 times A. This is a matrix, this is a matrix. Then let's multiply E2 with this matrix. So here we get E2 is 1, 0, 0, 4, 1, 0, 4, 1, 0, 0, 0, 1. We multiply this one with 2 minus 1, 0, minus 1, minus 4, 5, and 1, minus 3, 2. Okay? And then let's see what we get. This is going to be equal to 1, 0, 0 times 2 minus 1, 1. We get here 2. Then we have minus 1, 0. So these don't change. And then here we have 4 times 2, 8. 8 minus 1, 7. Then here we have 4 times minus 1 is minus 4, minus 4, minus 8. And then we get 5. And the third row does not change much because we have 0, 0, 1, which is going to multiply. So if we multiply by 0 the first two elements each time, we get nothing. By 1, we multiply only these. It's 1, minus 3, 2. So this is equal to what? This is equal to, how can we represent this operation here in matrix notation?
E2 times A.
Say it again.
E2, A2 times A.
Times A. This is not A. This matrix here, we got it from matrices. Okay? Would you agree? Would you agree?
Yes.
Okay? So this result that we get here, it is E2, which is the elementary operation here, which in fact this E2 corresponds to this, times E1 times A. And E1, it is this matrix. But then we can go a little further, and we notice that this matrix here is equal to this. Can you see that? So we started with A, and we got another A. So we see that this, what does this mean for us? We know that from here, we can say that E2 times, so E2 times E1 times A. For matrix multiplication, once you have a series of matrices that are being multiplied, it does not matter which one you multiply first. So if you have here 2 times 3 times 3, this is equal to 2 times 3 times 3. So you get here 2 times 9, you get 18. 6 times 8 is still, sorry, times 3 is another 18. So this means that this is E2 times E1. So we can also do this. We multiply these two together times matrix A. Now, if this is equal to A, What does this mean? What are these two matrices?
Equal to an identity matrix.
That's correct. So the multiplication of these two matrices, it has to be an identity matrix. But in the first week of this semester, we mentioned that when two matrices multiply and we get an identity matrix, we call these two matrices inverses of each other. Okay, so they are inverses of each other. And now, since we have E1 and E2, they are written here, we can even multiply them. So allow me, I was going to write it down here to look good, but probably we already have them written here. We can easily calculate it. Let's try to find what is E1 times E2 as a matrix multiplication. So let's go, let's check. We have the first row, we multiply the first column, we get here 1, and then this is 0, 0, because we multiply the first row with this, the first column, we get 0. Then we multiply the first row with this third column, we get another 0. Then we come here. What we see here is that now we multiply the second row with the first column. Okay, we multiply with these, and we get the following: 1 times 1. Wait a second. So this is this is minus 4 times 1 is minus 4 plus 4 0. So we get here 0. Okay, and then what is the rest? Here we get 1, and then we get 0. Then we multiply the third row. This is how we do multiplication. Multiply the first, so we get here 0, 0, 1. So it looks like E1 times E2 is really equal to identity matrix. We call this one I 3 by 3. Okay, so this is equal to identity matrix times A. So we also saw a demonstration, so to say, of how several linear functions that are applied on a vector, how they can be combined together and be applied again on the same vector. So a good exercise would be that with this number from 1 to 9, adding also the 0, when you multiply it with 23, the result, it is equivalent as finding all the possible permutations, okay, and determining all the elementary matrices, which they are simply row inversions, and then multiply them together. So yeah. Now let's see for a moment. Yeah, this is what you want to say. So it looks like these two row operations, they are inverses of each other, because this one undoes what R1 did, or R1 undoes what R2 can do. Okay, and these can be represented by these matrices. But I hope that now it is clear that the elementary matrices we always obtain those from the identity matrices. Okay, so I hope this is clear. Now, the moment that now these matrices, let's assume that this is matrix A, okay, or actually we said that this is A, let's not get confused, and let this be B. Now, matrix A and B, we call this row equivalent, okay? Row equivalent because we can obtain A from B using, so here we can say A and B are row equivalent. Since A and B can be described using a limited number of elementary matrices. Okay, so if there are elementary matrices like these, which let me say, which can be obtained by multiplying an elementary matrix EM, then we call these row equivalent. So if you look at the common sessions, for example, let's look at the last example given by Adam. He said that if we multiply this number by 23, what we can say here is that the number starting from 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, this one, and the other numbers, which is 2, 8, 3, 9, 5, 0, 6, 1, 4, 7, these two, they are row equivalent. Okay, maybe this is the way to say it. Okay? So I think it should be rock solid in your minds of what we are talking about. So yeah, those are row equivalent, which means that you can follow 10, 15, 20, 50 elementary row operations on a matrix. In the end, whichever matrix you started with, in the end, you're going to get a row equivalent matrix because they are linked together using EMs. EMs are derivatives of identity matrices, and that's all we can say for now. Now, so it looks like, let's give a couple of definitions. Now, with these discussions and these examples that we went over, but let me ask, sorry, I have also one thing to consider. Now, if we started from a series of numbers, from 1 to 9, you multiply by 23, you get a permutation. Now I can ask you the following. Can division by 23 be represented by an elementary row operation? How can you answer this question? So my question was this. Can the division of the number that was acquired by Alan Petro, can the division by 23 be represented by elementary row operations? I mean, it's a simple yes or no, 3 letters versus 2 letters.
Some
Yes.
numbers don't repeat, yes.
Yes, okay. Yes, and now what is interesting is that writing division in a computer is a very expensive operation. It's very difficult to divide numbers. Okay, so if you program division of numbers in the hardware language of the computer, this is a very tough question. But now you have done the division of a huge of numbers. You are defining the division by elementary row operations, so you should be proud of yourself. It's very difficult problem to do in principle. Okay, even division of two matrices, which is defined as a in principle, it's a very tough problem because before doing the division, for the sake of computational complexity, it does a lot of checks. It checks whether the matrix is upper triangular, it checks whether the matrix is diagonal, it checks for other properties, and then it starts doing the calculations. And calculations they take a lot of time, but in the end, you always have some good, unique examples, like the one that you have answered yourself, such as multiplication by 23 or 15, and division by 23 and 15. So we can represent all of these with matrix multiplications. Now, during the discussion so far, I think you also had a very important input when you said that a matrix multiplied by another matrix, you get identity matrix. That means that these two are inverses of each other. Now, the theorem that we are going to mention today. I hope so far we made a clear statement of what we wanted to come to. But with this good exercises, let's say this theorem of the first theorem of today. So if A is an n by n matrix. So this is how we read this. So any matrix A, if it is n by n, okay, n rows and columns, all statements are equivalent. Okay, if A is n by n, all statements are equivalent. So the first one is A inverse exists. So we're saying all statements are equivalent. This does not mean that matrix A has an inverse, but this means that if this exists, we have also the second statement that follows, which is AX equal to B has a unique solution, has for all B's a function of Rn. Okay, so what do you understand from this sentence? In the previous sessions, we have done here in the class the solution of linear systems of equations, which were represented by this expression, Ax is equal to B. Okay, And for this system of linear equations, we had the option where we had no solution at all, okay? But it looks like if the inverse of a matrix exists, then this always has a unique solution. Actually, when we say it's a unique solution, that means that what can you conclude from here? Some of us might remember that having a unique solution, this means that we have no free variables in reduced row echelon form, okay? This is just some little bonus sentence which all of us that have been very attentive and know how to, and we have understood very well the solution of systems of linear equations, this should become to us a little trivial or easy to pick it up, because we know that whenever we try to solve these systems, we try to reduce the original matrix into a matrix which had a lot of ones, like leading elements and so on. And it looks like a unique solution would be, in this case, you can go back to the notes and try to understand this a little better. So the third statement is the following. AX is equal to 0 has only the trivial solution. What is the trivial solution here? I want an answer from you. So, what is the trivial solution in this case? AX is equal to 0. 3x is equal to 0. What is the solution? What is x? Sasha x is. Sasha pani obratu?
0.
0.
Good. So also here, thank you. So this works also here. So the trivial solution for any matrix multiplication by x equal to 0, you always have the trivial solution. You could have more solutions, but if the inverse exists, you have only this. This is the only solution. Thank you for your feedback. And the fourth case is that reduced row echelon form of A, this is equal to the identity matrix. Okay, this is the fourth statement. Now all of these are equivalent. Again, what do you see from here? If A is a square matrix and we know only this, okay, let's say you are in the exam, you have a matrix, you try to produce ones at the beginning of each row. You simplify it as much as you can, and finally, if you get identity matrix, this means that the inverse exists. This means that AX is equal to B has a unique solution. First of all, having a solution is very important. If a system has a solution, the system of equations is called consistent. But more than that, it will have a unique solution. Now, how do you read this one actually? Now, this is a theorem, that's all. But if you look a little carefully, we can say that we start with the matrix A, okay? How do you get the reduced row echelon form? You apply an elementary operation E1, right? Then another elementary operation E2. How do you do this? You do this, row 3 is equal to row 3 star plus 2 row 1, okay, so it goes forward. You pick the pivot row at the top and you change the numbers, the rows below. Once you go this cycle, you go to the lowest row and you make it as a pivot to change the elements above them, right? So you can have a few of these. This is E4, so these are all the elemental operations which this applies on this, and this on the output of so far, this one on the rest. And in the end, you're going to get something like this, okay? So this representation, I think it's clear to all of us. And now, it looks like, how can we argue a little further? So in this way, actually, what can we conclude from here? So imagine for a moment, let's say we stop at EN, okay? So we said that from A, we apply this elementary operation E1, that's good, but at the same time, in the end, we said that we can also multiply them like this. In this case, what is the multiplication of all of these elementary operations?
Elementary matrix.
Thank you for answering, but think about this one. You have a matrix here times A, you get an identity matrix.
A inverse.
Correct, that's correct. So this is A inverse, so that's good. We have here A inverse times A, this is equal to identity matrix. So how can we find the inverse? So inverse actually, it could be something difficult. I remember we did in the first week examples of this nature, like 1 minus 2, 7, 5. We said, what is the inverse of this matrix, right? So we memorized some trick, which I forget most of the time. So what was the inverse? If this was A, and the A inverse is going to be the following. This would be equal to 1 divided by 1 times 5 minus the multiplication of these two. So we multiply them like this. I think this is 1 over 5 minus 14 minus 14. This is 1 over 19. And then whoever, maybe someone of you in the class remember this. I forget. I think this is 5, 1, 2 minus 7. I think we interchange these two and we put a minus sign on the other column. So this is the inverse, okay? So this is something often we could memorize it. Memorizing is not always the best thing to do it, but this would be the case. But if the matrix is large, it's larger than 2 by 2, the matrix can be 7 by 7. Then how can we identify the inverse matrix? It looks like we can look at all the elementary row operations that you did. So you are in the exam and you report the step-by-step how you do the reduced row echelon form. And then what you can do is that you get all of these matrices, you multiply them together, you find the inverse. You see? So even finding the inverse of a matrix, apparently, it's easy. There is a general way how to find the inverse. I find it personally very difficult. You need to memorize the procedure. It's not difficult. In linear algebra, the most difficult thing is this. Is 1 times 5 minus 7 times minus 2. It is the most difficult thing. There is nothing difficult here. But to me, it seems a little huge work, plethora of work. But okay, so let's move again. Let's see what is next. So okay, so we just defined so far only how we can visualize, how we can try to figure out the idea of the inverse. And I wonder if we can okay. In fact, it would be good if we so let's assume we are in the midterm. This is an exam, and we need to solve under stress the question of finding the inverse. How can we do it? Let's say that someone gave to us this example. Generally, the lecturer of the class gives us an example which looks like this: minus 1, 1, 1, 2, 0. So, and we say find the inverse of this matrix. Okay. So if we need to find the inverse of this matrix, we merge this one with 1, 0, 0, 0, 1, 0, 0, 0, 1. So the question is, given this, A inverse is equal to a question. This is the question. So let's start. How can we do it? A good trick, sorry, a good trick would be to interchange row 1 with row 3, because we need to have a leading one, right? So let's follow this. This is 1, 2, 0, 0, minus 1, 1, minus 2, 1, 3. Okay, first step. Let's do the same thing in the identity matrix here, which is going to be 0, 0, 1, 0, 1, 0, 1, 0, 0. First step done. Second step, we need to make this 0. How can we make this 0? The function is going to be row 3 star is equal to row 3, then what? Can somebody help me here?
Plus 2R1?
Thank you. Yeah, exactly. Plus 2R1. Because this is minus 2. How to make this 0? You just add 2, right? So then, let's see. We get here 1, 2, 0. 1, 2, 0. 0, minus 1, 1. And then we do here, minus 2 plus 2, this is 0, okay? Then we have 1 plus 2 times 2, 1 plus 4, this is 5, and this is 3 plus 2 times 0, this is 3, okay? Then let's do the same thing here. So this is the identity matrix. This is 0, 0, 0, 0, 1, 0. Now let's modify. Now we are modifying also the identity matrix that we merged to the original matrix, the same way that we used to construct the augmented matrix where we merge the A and the B, where the B is the answer vector. So this important useful things, techniques that we are learning, let's see what we get here. We get row 3, which is 1, plus 2 times row 1. This is still 1. Then 0 plus 0, 0. Then this is going to be 0 plus 2 times this one is going to be 2. Okay? Then the next step is we try, so we found one leading one. The next one, we try to get a leading one here. How can we get a leading one here?
Row 2 times minus 1.
Yes. Now, allow me to do this on the board, which means multiply by minus 1. I can make this plus 1, minus 1, minus 1. Okay, we got a leading one. Now, the next step is to make a 0 here. How do we make this 5, 0? We say here, row 3 star is equal to what? Row 3.
Minus 5 row 2.
Yes, exactly. Minus 5 row 2. And then here we move ahead. We say 1, 2, 0. 0, 1, minus 1. And actually we can write the rest. So we keep the first row is not affected. 0, 0, 1. 0, minus 1, 0. Now let's apply this modification. We say row 3 is equal to row 3 minus 5 row 2. This is 0. And then we have 5 minus 5, 0. That's what we were aiming to do. 3 minus 5 times minus 1, we get 3 plus 5, 8. And then we have row 3 minus 5 times this is 1. 0 minus 5, we get here 5. And then we have 2 minus, this is 2. Okay, what is the next step? We need to make a leading one here. How can we make a leading one?
We divide it by 8.
Yes, we say row 3 divided by 8. This is 1. This is used by HRA, 1 over 8. This is 5 over 8. And this is 1 over 4. Quadratic. This is a quarter. Okay. Then, what is the next step? We try to make these zeros. How can we make these zeros? We use this as a pivot. And this will be, we say row 2 star is equal to what? Can you help me here? Row 2 star, we want to make a 0 here. What would be
plus row 3?
Exactly, plus row 3. So we have this one on top of here. So here we're going to have 0, 0, 1. Since this is the pivot, this is not changing very soon. Okay, so here there's going to be 1 over 8, 5 over 8, and 1 over 4. Then row 2 is 0 plus 0, 0, 0 plus 1. We just add them. It's an easy operation. This is 0. And then here we have 1 over 8. Minus 1 plus 5 over 8. What is it? It's minus 3 over 8. Sorry, this might become a little congested, but you can follow me from your notebooks. And then we add these two together, we get a quarter. Can we try it together? Okay. This is a 0. Apparently, things are done. So we just write here 1, 2, 0, 0, 0, 1. What is the next step? Next step is we need to make this a 0. How can we make this a 0? We can say that row 1 star, the modified version of row 1, is equal to row 1, then what?
Minus 2 row 2.
That's good. Okay, thank you for the comment. So then let's move here. We move to this part and we say that This is 0, 1, 0, 0, 0, 1. So the bottom two rows, it will not change. This is 1 over 8, minus 3 over 8, minus 3 over 8, 1 over 4. Then the third row is again 1 over 8, 5 over 8, 1 over 4. Okay, then let's see what we got here. 1 minus 2 row 2, this is 1. 2 minus twice times 1, we get a 0. This is also 0. And let's see. Row 1 minus 2 row 2. So this is going to be 0 minus 1 over 4. Okay, so this is minus czerek. Then here we get 0 minus 2 row 2, which becomes plus 0 plus 3 over 4, right? So this is 3/4, okay? And then we get here 1.
Professor, I think 3 over 8.
Here, let's check. This is 0 minus 2 times minus 3 over 8, okay?
Yeah, I thought it was minus 1. So
Very good, okay. So this becomes 0 plus 2 times 3 over 8. So you get, what is this? 3 over 4, okay? This is 3 over 4. And then we have 1 minus 2 times 1 over 4. That's 1 minus a half. So we get a half, 1 over 2. Okay, so it looks like, what do we observe here? We started from at this part, and we had the following. We had AI, we had the matrix A and the identity matrix I. We applied a series of elementary matrices, okay, to A, but we applied them also to I, right, to the identity matrix. So if we apply here elementary row, so let the EM, some такими шум M, и чунтита M. Okay, let's call it elementary matrix operation E. Now, in fact, this is equal to, for visual purposes, let's assume that this is equal to EA, because we apply this one to this matrix, and at the same time, we apply this matrix to I, okay? Now, this E times A, what did we get? We got the identity matrix here, so we can continue. So this matrix that we applied here, this is identity matrix times this matrix, let's call it, I don't know what we can call it, but of course we can come up with some names. Probably more than 3/4 of the class know what it is. But this is the identity matrix, and here we ask the question, how is it possible that E times A is equal to I? So it looks like E times A is equal to I. Would you agree that this is the case?
yes.
Yes, because that's what we got. So apparently, this E is equal to the inverse of A, right? So this E is equal to inverse of A. So if this is the inverse of A, then we write it like this. We say inverse of A times the identity matrix. Then this is equal to what? Inverse of A times identity matrix is equal to what?
Inverse of A.
It does not change because identity matrix is really multiplied by 1. So we see that this is identity matrix times A inverse, okay? So it looks like if we start from here, we move this way. This is just an argument we made to argue this statement. So it looks like this is equal to I A inverse. Okay, so in A inverse apparently is this component here. So we found it. Then we know some nice matrix properties, which is the following. A matrix multiplication by a constant is a well-defined operation. So, and also dividing by a constant is also a well-defined operation. So, for just out of curiosity and to save some space, we could write the following. We can write this is the let me write the A inverse right away because I don't want to rewrite everything. let's factor out. What can we factor out from here? We can factor out 1 over 8, okay? Then we can rewrite this one as what? Minus 2, 6, what is this? 4, then 1, minus 3, 2, 1, 5, 2, okay? So this is the A inverse. So let me think. Now there is one question. What could be this number? What is this 8? Fine, well, this is equal to A inverse. Okay, that's good. We learned. So by now, you know. So if you come, you can check actually how long it took for us to derive this one. It was not that difficult, and we found out this one. So whenever you go to an exam or to a homework, it's easy for us to calculate this one. But then the question is the following. What could this be? In the case of a matrix of 2 by 2, how this was, we just memorized that expression, right? So it's not that we derived it. We just said that for any matrix AB, CD, what was the inverse? The inverse, it was 1 divided by A times D minus B times C, right? Times, I think it's DA minus B minus C. So the same question remains, which could be of the form, what could this number be? This number that we saw it in the first week of the course, we solved a couple of examples and so on. And I remember I asked in the class, when there is a very unfortunate possibility where the inverse of a 2 by 2 matrix does not exist. I asked this in the class, I said, for any matrix 2 by 2 which is represented by this one here, for what unfortunate case we would have no inverse? I got an answer from the class, we stated that, oh, professor, if this product is equal to 0, since division by 0 is not defined, we don't have an, we don't have an inverse. I said, I think I believe you are right. So in case AD minus BC, if this is equal to 0, then we can conclude that A inverse is not defined. We cannot find it. It doesn't exist. Actually, it doesn't define. Let's say defined. Okay? The better word is the following, is that actually this one doesn't exist. Now, the question is, what is the relationship between this factor here and this factor here? Is it any relation at all? We're going to try to figure this out. And we define, let's move forward. So I think we are good so far. Let's move to the next piece of material. So we define the new variable, determinant. Determinant, we denote it, we write it like this. We say determinant of A, we denote it also like this. So in this course, if you see the absolute value looking like a shape across a number, this is the determinant. Now, but before we do this, it's always good to have a definition. So for any matrix which looks like this, A, B, C, D, determinant of this, so A is equal to this, determinant is equal to AD minus BC. Okay, so this is how we we define the determinant for a 2 by 2 matrix. For a larger matrix, let's assume that we have a matrix which looks like this. Minus 2, 3, 2, minus 5, minus 1, 0, 1, minus 2, 3. So if this is another matrix, the determinant of this one is equal to minus 2 times, so we can do
The matrix 3, 2, minus 1, and 3.
3, 2, minus 1 and 3. Can you repeat it again?
No, sorry. If we take the determinant minus 2, it's minus 2 times the matrix minus 1, 0, minus 2, and 3.
Yes, minus 1, 0, minus 2, and 3. But we have to multiply this one with the determinant of this little thing. Okay, you are correct. And then we move to the next element, which now becomes minus 3. Times the determinant of which matrix?
Minus 5, 0, 1, 3.
Yes, minus 5, 0, 1, 3. And the rest is plus 2. Plus 2 times, so we are using this 2. If we use this 2, we take away the row of 2 and the column of 2. Okay, so we take away where the 2 is, and what is left is minus 5 minus 1, 1 minus 2. Okay, and then we use now the correct expression here, in fact, is the following. Find indexing after minus duše. What row, what column is this minus 2?
Is the second column?
Third
No.
row, second column.
Yes, it's third row, second column. That's true. So this minus 2, so we can say A 3, 2 is equal to minus 2. Okay? And then that's true. And now, if we use this one to find the determinant, we have a parameter which we write it like this: minus 1 to the power 3 plus 2. Okay, what do we get here? Minus 1. Okay, now let's pick up this 3. What is A33? A33 is 3, right? So we can define a product which is minus 1 to the power 3 plus 3, which is the indexes here. This is equal to what? Plus 1. Let's pick this minus 5. What is A? 2, 1. This is minus 5. We can define a factor which, dar șpiegăm să ne blochăm, utilăm și coi nevoie with this. So we can define a factor minus 1 times the factors of A, 2 plus 1. Okay, so what do we get here? Minus 1. Now, here, when we use these factors here, all of these, in fact, they are always multiplied by minus 1 to the power 1 plus 1. Okay, because then this in fact is plus, it's we write it minus 3, but it is in fact plus minus 1 times 1 plus 2, okay, times the 3 itself. So, but what is this multiplication? We get minus 1 to the power 3 is minus 1 times 3. That's why you get a minus 3 here. So you can either remember it like this. Is it clear what we try to do here? I believe yes.
Yes.
Okay. Now at the same time, we can also define a matrix which looks like this, where this is plus minus plus, minus plus minus, plus minus plus. Okay. Or you can remember this. So if you have to use any element in a matrix which is 15 by 15, I'm going to give a question where you have a matrix 15 by 15 in the final exam. So get ready for it, okay? So, if you are somewhere in the matrix, what you do is that you just walk 1 plus 1 for the beginning. You start with the plus sign, plus minus, up you go there, okay? So you can either visualize this and this, Or you can do this -1 to the power of the indices of the matrix element. So -1 to the power of the sum of those two indices times the number. Okay, so we also covered this interesting, unique step. So help me here. What is the determinant here? We define this. If it is 2 by 2, this is what it is. So what is the determinant here?
6.
-3. Do you have much objection for this? It's -3, right? What about here?
-15.
-15. What about here?
$11.
11, that's true. If it was Donald Trump, he would say 11. Okay, so it'd be a little different, but this is 11, not 11. So here we get -2 times -3, this is 6. Then here we get -3 times -15, this is +45. And here we get another +22. Okay, this is the determinant of the 3 by 3 matrix, which is equal to 67, 73. Okay, so this is the determinant, which is 73. So we define this quantity. Now, to find the inverse of a matrix, we have another step of another procedure, which takes some operations to follow. But let me see if we can do an example like this. It's also determinant. Okay, so now I hope determinants are clear. Okay, so we have to give a series of definitions. First of all, we have a matrix A, and we want to find the inverse. The inverse of a matrix, it exists only if the matrix is square. So if it's going to be a square, you can read it like this. If you see this notation on the board, you know this is a square matrix. If you write it m by n, it's not a square matrix. Or it might include the square matrices in it, in the case of m is equal to n. Now, the first thing we need to do is that this is the matrix n by n. Then we define a minor Mij. Okay, we define the minors. Then after the minors, we define cofactors, which is Cij, okay, is equal to -1 to the power I plus j times Mij. Okay, so this is the step that we define the cofactors. Then, after the cofactor, we can define the adjoint. So let me think for a moment whether we should write the numbers. Okay, so after the cofactor, so we have this component or this quantity with cofactor. Then we define the adjoint, which we call this adjoint, is equal to cofactor transpose. Okay, so if we see this element Mij, where I and j they are numbers, this means that these minors they are matrices, a matrix at Vogel. Okay, cofactors. This is also a matrix because it involves the use of a lot of elements Mij. Adjoint is another matrix. Okay. So this is the adjoint, and then the inverse of a matrix. So we are following this path. We say that inverse of A is equal to the 1 divided by the determinant of A times adjoint of A. So this is what we need to keep in mind. So it looks like starting from the matrix A, we need to define some numbers which are called minors. From the minors, which they are called minors because probably they are smaller in dimension than the matrix A. Then we define the cofactors. What does it mean to find the cofactors? You produce a matrix which is plus minus everywhere, and you multiply with plus some indices, and you multiply by minus some other indices, okay? And you get this. Then you construct the transpose. You know what transpose is. The rows becomes columns, okay? You do them carefully, you get it. Finally, we divide this adjoint by the determinant, and we find the A inverse. So here you might have some hints. What is this 1/8 here, okay? So now let's see how we do it. So let's assume for a moment, let's give an example. A is equal to 1, 2, 3, 4, 1, 1, minus 1, 3, 0. Okay, so what is the minor? We just gave, we did not give the description of the minor because we want to keep it, we want to see the whole structure, what all we need to do, so that it does not become confusing, or so that we can follow up at which step we are. So the first thing, the minor is the determinant of the, let me write it like this, Mij is determinant of smaller matrix. Okay, after removing ith row, okay, and jth column. So Mij, what is it? They are numbers, but it will be the determinant of a smaller matrix after we remove the first row and first column. So let's try to determine these then. What is M11? Okay, what is M11? We remove the first row and the first column. What is the determinant of this little matrix?
1, 1, 3, 0.
Yes, but it's minus 3 because the determinant of this matrix is product of these two numbers minus 3. Okay. What is and then what is okay, I think we know this part. Let's find what is M23. M23, we remove the second row, okay, we remove this row, we remove also the third column. Okay, so we remove this second row and third column. What is this equal to?
It's 5.
What did you say?
5.
You said, okay, sorry, you said 5. Okay, that's 5. Because we have 3, 5. Okay, this is equal to 5. So this is how we can find this. Okay, so and the rest, you can also calculate, for example, I don't know, M12. What is M12? We remove the first row, second column, and we will be left with, so first row, second column, we get 1. Can you see this? So let me see, yeah. Now it looks like we find a matrix, minor matrix M, which is carrying these numbers. We have here minus 3. What we found M12 is 1. Okay. We found M23, which is going to be this was equal to 5. So we need to find this minor. If you substitute, if you check all the numbers, we are going to get this expression, which is, let me see, actually, it looks like I don't have the numbers here. Okay, so let's follow it like this. So we have minus 1, minus 3, 1. I just want to see if I have an example which we can cover. We get here minus 1, but did we do this is minus 3? This is okay. 3, 0, 1, 4, 1. Okay, so let's move like this then. So we have to work all the numbers because I don't have this one somewhere. So to find this one, for this form. What is this element? Who can solve this? We get 2 times 0 minus 9. We get minus 9 here. This element is 3. Then this number here is 2 minus 3 minus 1. This element, for 3, we remove this row and this column. We get 1
Plus
minus,
3. Plus,
minus what?
I thought it was 3. No, sorry.
Well, I mean, let's check it again. We remove this one and this one, but thanks for the feedback. It's going to be 1 times 1 minus 12. It's minus 11, okay? And this one, 0, it's 1 minus 8, minus 7, okay? Then this is the minors. Now, after the minors, we need to determine, let's see, we need to determine the cofactor. In order to get a cofactor, we multiply everywhere by plus and minus 1. So in this case, we just write here the C. This would be equal to minus 3, 1. We did not find this. This would be 12 plus 1, 13. This is 13. Then here we have minus 1, minus 3, 1, 13, minus 9, 3, 5, minus 1, minus 11, minus 7. So we found the cofactor. Then after the cofactor, we calculate the adjoint, okay, which is going to be equal to the transpose of these numbers. So the first row becomes a column, minus 3, 1, 13, minus 9, 3, 5, minus 1, minus 11, minus 7. And then from this adjoint, we have to divide with the determinant of the matrix. Now, I just want to see if the numbers look all correct. So that let me see the A23. Is the A23 correct? 1, 2, 3. Yeah, I think, okay, so this was also correct. Now we found the adjoint. So we did this minor, cofactor. We found the adjoint. Now we need to divide the adjoint with the determinant. What is the determinant of this matrix? Determinant of this matrix is going to be the following. 1 times determinant of 1, 1, 3, 0, okay? Minus 2 times the determinant of 4, 1, minus 1, 0, plus 3 times the determinant of 4, 1, minus 1, 3. Okay, so let's separate this one for a moment, like this. So here we have, this is 0 minus 3, this is minus 3. The determinant here, it's 0, it's plus 1, it's minus 2. Then here we have 12, 13 plus 13 times 3, 39 plus 39. This is equal to 39 minus 5. This is equal to 34. Okay. So then, now that we know that the determinant, we say that the A inverse is equal to. Now it would save me some time and some space, but from this adjoint, well, let's write it like this. No, let me write this the whole thing. This is equal to 1 over 34 times minus 3, minus 9, minus 1, 1, 3, minus 11, 13, 5, minus 7. And this is the A inverse. This is how we found it. Now, there is a small chance that this 1 over 8 division that we did in the previous example, that came out of our calculations, it could be the determinant of that matrix. You can have a look, okay? And it's a high probability. And you know why? Because this is something like, imagine for a moment, you have a matrix which is complex numbers, random numbers to some degree. And then, is it possible that all the numbers will be multiples of 7? Okay? So let's say you start with this matrix, or you can change these numbers a little, and imagine, is it possible that A inverse would be a number that looks like this: 7, 14, 21, 77, 77, this is 7, 14, 21, what is 7 times 7? Do you know what is 7 times 7?
42.
Huh? That's 42. So, is it possible that the inverse from a random numbers all to be multiples of 7? Now 7 is like the golden number, right? Like there is a golden ratio and there is 7, which the Parliament discussed it with very enthusiasm and dedication. So, it's a small chance that you might have multiples of 7, so to factor out. So, so probably this is the determinant of the matrix in the previous example. So you can go back to the example that we covered before like 30 minutes and check what is the determinant, okay? So that number, it comes up because we have this procedure, which in a short version, it's here. And the description you have in detail down here. And to make this a little more clear, we're making a lot of rhyme nowadays. Whenever you rhyme, people should run away because it's like the proverbs told by the Cathan Populi. So, do you have any question from what we covered so far? So we covered the elementary row operations. We saw an interesting example where you had the new permutation or a new combination of numbers is equal to the original number times a constant value or a factor. Now, this would be like your homework, okay, to figure out the, let's say, the elementary matrix which provides the multiplication of a matrix with the with another vector. Now, I wonder if you can do this one. Actually, in this class, you are a certain number of students. Can you see the list of the students in the class? Do you have any chance in the files around? Yes or no? Okay, because I could say the following. Depending on where your name is alphabetically on the list, you multiply that number 1 to 9 with your number in the list, and you solve your own exercise, okay? So this is probably how I'm going to formulate the homework. But if you have, do you have any question? Is everything clear?
Professor,
Yes.
at the last exercise, when we converted from minor to cofactor,
Yes.
shouldn't we multiply that with the plus minus matrix?
Yes, we should, and we didn't. Yes, that's true. It's good that you mentioned this one. I completely forgot about it, which is unforgivable. And yes, so in this case, this -3, this becomes, sorry, what does, no, this is plus, this is minus, and this is the new modification. This remains the same. This is going to change. This becomes plus, so this is updated. This is plus, minus, plus. This doesn't change. Minus, we put a minus here. This is updated. Plus, minus, plus, no change. Minus, this becomes plus. This is the updated. -7 is the same. Okay. But thank you for noticing this one. We mentioned it, but we completely forgot it. So we forgot this important step. So then we took the transpose. So apparently these numbers transpose. It's interesting. The transpose has affected these numbers. You can see where they are. Plus 15, minus 15. So we make this like this. This is plus 5, minus 1. Yes. You do the same change here, which I can do it like this, minus, plus, minus. Okay, we should not have forgotten this. Now it looks better.
I have a question.
Yes.
For example, in the incoming exams, for the last one that is a in power -1, the inverse one, do we have to substitute it 1 by 34? A do të zëvendësojmë atë të pjesa fundit aty.
Yes, you have to divide. You have to divide all the matrix by 34. Yes.
Okay.
Okay. And let's remove this. Pra, kur vinim si do të mësoni tabelën shumëzimit, mirë se kaq që duhet. E tabela e shumëzimit është element shumë për determinues kur voton, kur futesh në listë, kur shkon emri në listë të partisë, për shkak. Okay, if you don't have any more questions, we can come to a closing. I thank you for your attendance.